Okay, so let's move on with the concept of the hard and soft as a basic theory. So in the last class, we did a number of qualitative considerations in order to determine qualitatively what is a hard acid and what is a hard base. Now, of course, it would be very useful if we also had a quantitative concept that would allow us to attach a number to a particular hardness or particular softness. So there's one concept which I would like to discuss today, and this is the concept of the absolute hardness. So the concept of absolute hardness was developed by Ray Pearson, and he defined the absolute hardness of a substance as the difference between the ionization energy and the electron affinity of an acid or base respectively over two. And the softness would then be, well, just the inverse of the hardness. So the softness sigma would be 1 over the hardness eta. So you can immediately see that this hardness scale is related to an electronegativity scale that we previously encountered, which was Mulliken's electronegativity scale, which was defined as the sum of the ionization energy and the electron affinity over 2. So now what's behind of the idea of the absolute hardness? Why would the difference between the ionization energy and the electron affinity of an acid or base be related to its polarizability and its hardness? And that relates to a property of hard and soft acids and bases that we already previously discussed in the last class, which is that when we have a hard acid or hard base, then the orbit energy differences between the orbitals is typically large. Whereas when we have a soft acid or soft base, then the energy differences are typically small. Okay? So now the difference between the ionization energy and the electron affinity is actually nothing else but the difference between the lowest unoccupied molecular orbital and the highest occupied molecular orbital. Okay, so we take this energy difference as a quantitative measure for the hardness, because orbital energy difference, we know that orbital energy differences relate to hardness. Okay, so we can illustrate this here the following way by this example. So we have here again the formula that the hardness eta is equal to the ionization energy minus the electron affinity over 2, which is the same as the energy of the HOMO minus the energy of the LUMO over 2. So now we have here a series of acids. So these are just the alkali metal ions. So lithium plus, potassium plus, rubidium plus, potassium plus, rubidium plus, and cesium plus. So like discussed in the last class, we would expect that the hardness of these acids declines as we go from the lithium to the cesium. So now would the concept of absolute hardness back up that idea, and would it be able to define a quantitative value for the hardness? So we can easily see this when we look at the highest occupied molecular orbitals, or in this case we should better say the highest occupied atomic orbitals, or the highest occupied atomic orbital, and the lowest unoccupied atomic orbit because we are dealing here with simple cations. And you see here the energies of these orbitals. So for instance, for the lithium plus, why is it so loud today? The highest occupied molecular orbit here has this energy level of approximately 75 electron volts, and the electron affinity here has a value of approximately -5 electron volts. So now the energy difference, well, is just this energy minus this energy here minus that energy. So this is the HOMO and this is the LUMO. And that is the same as the ionization energy minus the electron affinity. Because the ionization energy is nothing else but to move the electron from the HOMO. Okay, so it's actually this energy difference. Okay, minus the electron affinity, which is the energy that is released in this case when we add a free electron to the ion. So a free electron always has zero potential energy, okay, and the energy that we gain is then the energy difference between zero and the binding energy for the added electron, okay, which is nothing else but the electron affinity. So if we subtract the electron affinity from the ionization energy, then we get exactly the energy difference between the HOMO and the LUMO. Now you see, for the 5 species we just discussed, this energy difference gradually decreases as we would expect. You see that in this case, the lowest unoccupied atomic orbitals have very similar energies, but you see that the energy of the highest occupied molecular orbitals increases significantly as we go from lithium to sodium to potassium to rubidium and to cesium. So you can see that using this concept, we can now attach quantitative values to the hardness of particular species. And we can do this for many species, and we can arrange, well, the hardnesses and the softnesses in lists, tables, so that we can make direct comparisons. Okay? So now you see here such a list. So you see here a number of cations, you see here a number of neutral molecules, and you see here a number of anions. So you see here the respective ionization energies. You see here the electron affinities. And you see here the associated hardnesses, which are nothing else but the differences between these two values divided by 2. All right. Now let us analyze the values that we get for a number of species and see if they make sense and if we can get additional information from the concept of absolute hardness that we couldn't get when we just did our qualitative analysis. All right. So you see that in the series of the cations, the aluminum 3+ ion here comes out as the ion that has the highest hardness value of 45 in this 45.77 in this case. So you would not be surprised that the aluminum 3+ comes out of as a very hard cation, because aluminum is a fairly light electron and has not very many electrons to begin with. And as we remove electrons to form cations, of course, our species highly contracts. So aluminum 3+ ion is indeed a very small ion, and for that reason, we would certainly understand that this ion has a high hardness. Okay, then you see that lithium comes next. So the lithium has a value of 35.32 of absolute hardness. So of course we would have expected that the lithium ion is also a very hard species, but I would not have been absolutely clear cut whether the aluminum 3 plus or the lithium plus would be the harder species. Okay, so the lithium atom is actually a smaller atom than the aluminum atom, because the lithium is in the second period of the periodic table, where the aluminums are in the third one. However, the lithium has only one charge, while the aluminum has 3 positive charges. Okay, so therefore, by just qualitative analysis, you wouldn't know actually which one you should consider to be the hardest species. Qualitatively, would certainly say that both species are hard species, but which ones is harder would not be clear. And you see now that the concept of absolute hardness gives you an idea which one of the two you may want to consider to be the harder ones. And you see that in this case, the high positive charge of the aluminum trumps the smaller atomic radius of the neutral lithium atom in comparison to the aluminum atom. So we can also check if relative absolute hardnesses come out as we would predict this from qualitative considerations. So for instance, you can compare lithium plus, sodium plus, and potassium plus. And we would, of course, expect that the sodium plus and the potassium plus, the sodium is softer than the lithium, and the potassium is softer than the sodium. And you see, this comes out correctly when the concept of absolute hardness is applied. You see the sodium has an absolute hardness value of 21.08, which is smaller than the hardness of the lithium. And you see that the hardness of the potassium is significantly smaller than the hardness of the sodium. Okay, we can also look at some ions we would consider to be quite soft and see if the concept of absolute hardness would classify them also as soft acids. So you see here, for instance, silver and gold. So silver, in particular gold, are period 4 and 5, period 5 and 6 elements. Okay, so they are fairly large atoms to begin with. Then we only remove one electron. So we have lowly charged metal cations. We would therefore expect that these come out as quite soft. They should certainly come out softer than, for instance, potassium plus. Then you see this is indeed the case. The silver plus is a hardness which is only about half the value compared to the potassium plus, and the gold plus is even softer. It has a hardness of 5.6, which is also significantly lower. You see also that the expected hardness of gold plus relative to silver plus is coming out as expected. So the gold plus is softer than the silver plus because the gold is in the 6th period of the periodic table, while the silver is in the 5th period of the periodic table. All right, so now we can also compare a number of neutral species. So with the exception of the BF3, all the other species, neutral species here, are typical bases. Only BF3 can actually interact as an acid. You see that the BF3 has a value of 9.7. We had in the last class said that BF3 would be considered a hard acid. So this is also qualitatively confirmed, but you see that in relationship to the alkali metal in earth alkali metal cations, it's not as hard. Okay, so even the potassium plus, which is already in the fourth period, we have a significantly harder, significantly greater hardness in comparison to the BF3. So you see from this that an actual positive charge on a species has a really great effect on the hardness. So it makes it significantly harder in comparison to a neutral species like the BF3. So now let's compare here these other species. So they are typically bases. So from qualitative considerations, we would expect that H2O and NH3 are hard bases, whereas PF3 and pH3 would be soft bases. And that is confirmed by the respective values. You see that H2O has a hardness of 9.5 and NH3 is a hardness of 8.2. As expected, also the hardness of H2O would come out larger than the hardness of NH3, just because the oxygen is smaller donor atom in comparison to the nitrogen, as we discussed also previously. But you see that PF3 and pH3 have significantly smaller hardness values of 6.2 and 6.0. We can explain the difference between PF3 and pH3 again by the electron withdrawing nature of the substituent. So the fluorine is significantly more electron withdrawing than the hydrogen. So the electron withdrawing effect of the fluorine makes the phosphorus atom somewhat smaller. Therefore, it's less polarizable, and for that reason, the species becomes harder. Whereas the hydrogen is not as electron withdrawing, and the respective phosphine is somewhat softer. But you see that the effect is not even particularly great. So last but not least, we have here these ions, fluoride, chloride, bromide, and iodide. So within that series, you would certainly expect that the hardness decreases significantly from the fluoride to the chloride to the bromide to the iodide, and that's also exactly what we see. The fluoride has the greatest hardness of 7.01. The hardness of the chloride ion is somewhat smaller. The hardness of the bromide ion is even smaller, and the iodide ion has the smallest hardness value overall. It has a quite small value of 3.70, so it would really be a very, very soft base. So you can see here again also the effect of the charge. In this case, we have a negative charge, and you see that this negative charge has a significant impact on the softness when you compare the values of these anionic species with the values of these neutral species here. So for instance, even though the fluoride or the fluorine is actually smaller atom than the oxygen, because the negative charge at the fluorine atom, we have a lower hardness value of the fluoride in comparison to the H2O and even the NH3. We see again that a charge has actually quite big effect on the hardness of softness of a species, and that also explains the extraordinary low hardness of the iodide. Not only iodine is a very heavy atom to begin with a lot of electrons. The negative charge at the iodine further increases the softness to a significant degree. Okay, I see there's a question here. Because there's a very wide range of values, is there some sort of value differential that determines a hard-hard interaction versus a soft interaction? Well, that's a good question. The answer is there's actually not a clear cut-off. So I'm not aware that in the literature there's a cut-off in absolute hardness being defined that would tell you when an interaction is still a hard interaction versus a hard-soft interaction. So therefore, when we define whether we have a hard interaction or hard-soft interaction, it's sufficient to use the qualitative considerations that we used in the last class already, just saying whether a species should be considered to be rather hard or rather soft, and then just based on these qualitative considerations, define whether we have a hard interaction between the two species or a hard-soft interaction between two species. Joseph, does that answer the question? Okay, very good question. All right, then let us now go from the theory to applications. I told you in the beginning of the last class that the hard and soft acid base concept is extremely useful to estimate whether an interaction between two species is strong or weak. And that can be used in order to determine a number of properties of substances. For instance, solubilities. So for instance, the solubility of the following silver salts here occurs in the following order. So the silver iodide is very insoluble, it's the lowest solubility, followed by the silver bromide, followed by the silver chloride, followed by the silver fluoride. So now we can explain these solubilities through the hard and soft acid and base concept. So the silver itself is a soft species, so it should make the strongest interactions with another soft species. Okay, so therefore the softest ion in the series should lead to the smallest solubilities. Okay, because when we want to dissolve a substance, then we have to dissociate the ions, and the stronger the interaction between the ions, the smaller the solubility should be. Okay, so the iodide is the softest of the species. Therefore, they will make the strongest interaction with the silver plus, which is the soft species itself. For that reason, we would expect that it's the hardest to dissociate the silver plus and the iodide. And for that reason, we would expect the smallest solubility. Okay, based on the same considerations, the silver fluoride should have the largest solubility, and that's also what is experimentally observed. All right. So in this case, the experimental solubility is in accordance with the HSAB concept. However, this is not always the case, or at least additional considerations need to be made in order to explain a solubility correctly. So, for instance, we could ask what solubilities would be expected for the lithium halogenides according to HSAB. Question to everybody. What should be the least soluble and what should be the most soluble? So we compare here lithium fluoride, lithium chloride, lithium bromide, and lithium iodide. Oops. Oh, that's the feedback. Oh, this I did not expect. Consider this experiment number. Sorry, the lithium fluoride. Yeah, that's correct. Can you explain why? Can you explain why you consider the lithium fluoride to be the least soluble?
Lithium would be a rare species in fluoride.
Correct. So in this case, we have a hard cation, which is the lithium plus, that would make the strongest interaction with the hardest anion. So in this case, the hardest anion is the fluoride, and therefore the lithium fluoride should have the lowest solubility. Okay. Then which one should be the highest? Should have the highest solubility? Well, that should be then the lithium iodide. So now let's see if that is actually realistic or observed by experiment, and the answer is not quite. Okay, so the lithium iodide is actually is having an unexpectedly low solubility. All right, so lithium fluoride, lithium chloride, and lithium bromide are in the correct order, but the lithium iodide has an unexpectedly low solubility. Okay, so that tells you that also other effects can determine the solubility. And one major effect to consider is, of course, the solvation entropy. Okay, not only is it important how much energy you actually need to separate the ions, but also need to consider what's the solvation entropy for the ions. So now the iodide is actually by far the lowest solvation entropy of all the ions of water. And that actually explains why the lithium iodide has such an unusually low solubility in water. Okay, so there is a way how you can use the HSAB concept nonetheless in order to also explain this exception. And to do so, you can try to explain solvation entropies also with the concept of HSAB. Okay, because when we have a high solvation entropy, then we have a high degree of interaction between the ion and the water molecules. Okay, and when we have a low solvation entropy, then the interactions are weak. So now the water, of course, has also hardness itself. Okay? So the water is a hard species in itself. So we can ask ourselves, with which anion would that water make the strongest interactions? Okay, since the water itself is hard, you would expect that it makes the strongest interactions with the hardest anion. Okay, and that would be the fluoride, but it would certainly make the weakest interactions with the softest anion, which is the iodide. So you see that you can explain the low solvation entropy of the iodide also with the hard and soft acid base concept. Okay. All right. I also wanted to point out that for this series here, you see a reverse of the solubility when you change the solvent from water to liquid ammonia. So by liquid ammonia, I do not mean an aqueous solution of ammonia in water. I mean really liquefied ammonia, cold liquefied ammonia. Okay, and that is because the ammonia is already significantly softer than the water, and it's actually soft enough to reverse the solubilities. So in liquid ammonia, actually silver iodide has the greatest solubility, and the silver fluoride has the smallest solubility. Okay, so the hardness of the solvent itself is also an important factor to consider. All right, then we can also explain the relative thermodynamic stabilities of ionic compounds. Okay? So whenever we have strong interactions between the cation and the anion in ionic compound, we would expect a high stability, and that would influence certainly properties like a melting point or a boiling point. Okay? So therefore, with the HSAB concept, we can also estimate whether you would expect a high stability or low stability or high boiling point or low boiling point or high melting point or low melting point. So we can apply this knowledge to alkaline oxides. So lithium oxide, sodium oxide, potassium oxide, rubidium oxide, cesium oxide. So which of these would you expect to have the highest stability, and which ones would you expect to have the lowest stability? Suggestions? So we basically combine O2 minus oxide with a number of different cations. So the oxide anion itself, would it be rather hard or soft? Remember from previous class, we said it was hard, yeah? So oxygen is a small atom, even if we add 2 negative charges, still a pretty hard species. So therefore, with which of the alkyl metal ions should it make the strongest interactions? An answer in the chat. The lithium, correct. So therefore, the highest thermodynamic stability would be expected for the lithium oxide, and the lowest thermodynamic stability would be expected for the cesium oxide. And that is also indeed what is experimentally observed. The lithium oxide has the highest thermodynamic stability. The cesium oxide has the lowest thermodynamic stability. You can see this also actually by the fact how the alkyl metals behave when you actually burn them in oxygen. So only for the lithium, you're actually getting lithium oxide. For the sodium, you're getting actually sodium peroxide. And for the other three, you're even getting superoxides. Okay, so this is another way how I can see that the lithium oxide has the highest thermodynamic stability, and that the thermodynamic stability declines as we combine the oxygen with the other alkali metals. All right. So we can also ask what we would expect for the earth alkaline oxides. So that should now be very easy to answer. So which, yeah, there is an answer. Beryllium oxide, yeah, that should have the highest stability, correct? Because again, the oxide is hard, and among the alkaline earth metal ions, the beryllium 2+ is the hardest, and the barium 2+ is the softest. Therefore, we would expect the following series. Beryllium oxide, magnesium oxide, calcium oxide, strontium oxide, and barium oxide. All right. Now we can also determine acidities. So we can, for instance, explain why the acidity increases as we go from water to H2S to H2SE. Can you imagine why the HSAB concept is able to explain this? So again, we can explain this using bond stability. So the H is certainly a hard species. So we have basically, we combine H+ ions with anions, O2- anions, S2- anions, and Se2- anions. Okay, that gives H2O, H2S, and H2SE respectively. Okay, so now H+ is naturally hard, so it would make the strongest interactions with the hardest anion, which would be in this case O2-. Therefore, H2O has the lowest acidity, H2S has an intermediate acidity, and H2SE has the highest acidity. Okay, so then we can also look at this series here. HClO4, HClO3, HClO2, and HClO. Okay, and the perchloric acid has the highest acidity, followed by the chloric acid, and then the HCl2, I've just forgotten the name, the chlorous acid, and HCO with the hypochlorous acid. Okay, so now in this case, it's a little bit of a harder task because all these acids are oxo acids. So in this case, the proton is always attached to the oxygen. And that's in contrast to the previous example where the proton was attached to different elements. So can you imagine how the HSAB concept nonetheless can explain that series? Okay, then I will explain it. So in this case, we can again argue with electron delocalization. Okay, so when we remove one proton from all these acids, we're getting anions with a 1- charge. Okay, now the species we create is the softer, the more we can delocalize that negative charge over the ion. Okay, so in the case of the chlorate, we actually have, well, 4 resonance structures that we can draw because we have 4 oxygens. Here it's only 3, here it's only 2, and here we have only 1 possibility. Okay, so for that reason, we can say that the perchlorate anion is actually the softest anion because the charge can be most delocalized, while the hypochlorite is the hardest one because the negative charge is most difficult to delocalize. And this can explain this case. All right. So last but not least, what about the basicity of Nh3 Ph3 ASH3? We cannot explain. Well, acidity we can also explain. Bronsted basicity by making very similar arguments. So that should now be easier. So which one of these should have the highest affinity for protons, which are hard? Sorry? No, it's not the arsenic, because the arsenic is actually the softest, right? So you would expect that the proton would bind most strongly to the species which is the hardest, okay? Which is then in this case the NH3, okay? Because then the bond is the strongest. So for that reason, the NH3 has the highest basicity, pH3 is intermediate, and ASH3 has the lowest basicity. I see there's a question in the chat. Yeah, the NH3, correct, Joe, yeah, correct. Very good. Sorry, I did not see you. Time. Okay, then this is the end of the chapter about the acid and base concept. So in the next class, I will start with the second part of this course, which will apply all the concepts that we have learned thus far to coordination chemistry. And we'll have a short break because next Monday is pacing break, and we will continue on Wednesday with the next class.